Hello everyone. Thank you for your interest in our paper with title, The Vertigo Effect on Your Smartphone, Dolly Zoom via Single-Shot View Synthesis. This work has been done by joint effort of Yangwen Liang, Rohit Ranade, Xuanquan Wang, Dongwon Bai and Jungwon Lee from Samsung Semiconductor Incorporated in San Diego, California. These days, cameras on a smartphone are more sophisticated than they've ever been. Mobile phones now come equipped with multiple cameras of different modalities. A typical setup may include 2 or more cameras with different focal lengths providing different field of views. In addition, a dedicated depth camera or sensor to provide long-range high-accurate depth information within the scene is also very common. Such setups take user photography to next new levels, and open up the possibilities of providing photographic effects previously not possible without special equipment. For example, possible applications include but not limited to 3D scanning and reconstruction, shallow depth of field portraits, Dolly zoom effect, etc. The Dolly zoom effect was first conceived in Alfred Hitchcock's 1958 film Vertigo and since then, has been widely used in movies. Therefore, such effect is often referred to the vertigo effect in the filming industry. To achieve this cinematic effect, the camera is moved either forwards or backwards from the subject under focus, while simultaneously adjusting the field of view in order to maintain the size of the subject in the frame. This leads to a continuous perspective distortion, with the most directly noticeable feature being that the background appears to change size relative to the subject. The visual appearance for the viewer is that either the background suddenly grows in size with detail overwhelming the foreground, or the foreground becomes immense and dominates its previous setting, depending on the way in which the effect is executed. Executing it requires skill, practice, and equipment. It is especially difficult with a mobile camera. Previous attempts at automatically simulating this effect required the use of a specialized light field camera, or capturing images while moving the camera. This paper presents a novel technique, to model this effect using camera geometry, and propose a novel synthesis pipeline to simulate the effect, given a single shot of single or multi-camera captures. Here, we define the single shot as image plus depth capture, as known as RGBD, from each camera at a particular time and location. The single-shot single-camera Dolly zoom synthesis pipeline is as shown in the figure. Here, the input is the image, denoted as I, with FOV theta and its depth map, denoted as D. We apply digital zoom to both I and D through inverse warping to a certain angle, say theta 1, to obtain the zoomed-in image I1 and the corresponding depth map D1. The original input image I and depth map D are reused as I2, D2 respectively. With our closed-form mapping formula, a synthesized image I1DZ and its depth D1DZ are produced from I1 and D1 through forward warping and Z buffering for a given index T in the image sequence. Similarly, a synthesized image I2DZ and its depth D2DZ are produced from I2 and D2 through forward warping and Z buffering for the given image sequence index T. Then the synthesized images I1DZ and I2DZ are fused together to form the fused image IF, while the synthesized depth maps D1DZ and D2DZ are similarly fused together to form the fused depth map DF. Then, occlusion areas in IF and DF are handled by our proposed depth-aware image in painting to obtain I bar F and D bar F. After view synthesis and occlusion handling, the shallow depth of field effect is applied to I bar F to obtain the final Dolly zoom synthesized image result. This effect involves the application of depth-aware blurring. To mimic the actual Dolly zoom effect, we also derived closed-form relationship between the size of the circle of confusion and the field of view relationship in the image sequence. The usage of shallow depth of field effect is twofold: 1. Enhanced viewer attention to the objects in focus, and 2. Hide imperfections due to image warping, image fusion and hole filling steps. For details of each block, please refer to our paper. The single-camera single-shot Dolly zoom synthesis pipeline can be extended to input images captured from multiple cameras at the same time instant with minor modifications. Consider a dual camera setup, where the inputs are the image I1 with FOV theta 1, and its corresponding depth map D1 from the first camera, the image I2 with FOV theta 2, and its corresponding depth map D2, from the second camera. In this case, the application of digital zoom in single camera pipeline is no longer required. The remaining of the pipeline remains the same. Now let's take a look at some of the sample results. For example, in this single camera single shot case, I2 is the input, I1 is the digital zoom version of I2. The Dolly zoom synthesized image sequence with shallow depth of field is shown with the dog in focus. In this example we demonstrate the capability of our pipeline for dual camera single shot case. As a conclusion, we have presented a novel modeling pipeline based on camera geometry to synthesize the Dolly zoom effect. The synthesis pipeline presented in this paper can be applied to single camera or multi-camera image captures. The focus of our future work will be on advanced occlusion handling schemes to provide synthesized images with subjectively greater image quality. Again, thank you for your interest in our paper. We also provide supplementary videos at the end of this presentation for your reference.